Welcome to Data Engineers Lunch number 100. I'm here with Alex from Dremio, and we're excited to present today's Data Engineering Lunch. Well, let's get started. Welcome to Data Engineers Lunch number 100. Don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. Today, we will be covering optimizing data, partitioning, sorting, compaction, row group sizing, and more. The co-organizers for this event are Rahul and myself. If you are interested in being a co-organizer, and want to help get speakers by reaching out to people in the data engineering community around the world, drop me an email. You could also drop us an email at marketing. If you are interested in giving a data engineers lunch or our sister lunch, Cassandra lunch, feel free to reach out to me for that as well. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of smaller groups, generally centered around data, and you can find out more about all various different groups and events at datacommunitydc.org. What do we cover in Data Engineers Lunch? We cover all things that talk or play well with data engineering. Data, Scylla, Dremio, key spaces, Cosmos DB, ingest, egress, all things data engineering. If there's anyone that would like to say hi, what brought you here, or what you hope to get out of this, drop something in the YouTube chat. If you're watching on YouTube, don't forget to like and subscribe, as well as turn on the notification bell so that you can be notified every time we go live. Our group rules: if you have a question, ask it. Be polite and courteous to others. Again, this is a respectful community, but we do want to know what your questions are. If you have the question, it's very likely that someone else does as well. And of course, share your knowledge. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. We've also recently done a lot of really exciting work with generative AI, and data engineering is absolutely our bread and butter. Thanks to our organizational sponsors, DataStax especially, and Dremio, thank you for being here, Alex. Thanks to George Washington University for providing venue space when we have in-person events. Thank you also to all of our organizational sponsors. If anyone has any job offers, you're looking for a job, you have a meetup or a conference or a hackathon that you want to promote, please take a moment and post them in the YouTube chat. We currently host Data Engineers Lunch periodically on Mondays at noon. We host Cassandra Lunch Thursdays at noon, and currently we also host no-code data and AI platforms some Wednesdays. We're always excited to share what we've learned and really look forward to these talks. Our most recent runbook was using Cassandra and Ansible to install Cassandra on AWS and Azure. And with that, I am very excited to pass the screen share over to Alex to get us started with our talk.
Hey, everybody, this is me, Alex Merced. And again, I'm a developer advocate out of Dremio. And today I want to talk about optimizing data, partitioning, sorting, compaction, row group sizing, and more. The idea is just to kind of give a tour of many of the different angles that we can approach our data, trying to think about like, how can we make this data a little faster? This is going to be a very high level talk, especially like geared towards those who might be like sort of like new to some of these topics. But again, my name is Alex Merced, developer advocate at Dremio. So I spend most of my days traveling around going to different conferences, meetups, writing blogs, putting together like tutorials on particularly the data lakehouse. So either whether it's just like implementing a data lakehouse, using different tools like Dremio, like Apache Iceberg, like Nessie, Arrow, et cetera, et cetera, et cetera. Just kind of showing people and then just talking about sort of the benefits of using these tools. I also host several different podcasts. I'm one of the co-authors of an upcoming book from O'Reilly, Apache Iceberg, the definitive guide. So you can scan that QR code to get an early release copy. So that should be coming out early next year, but you can get yourself like right now, I think right now it's like the first 180 pages about that's there. Okay, I also host several podcasts, Gnarly Data Waves, which is a weekly broadcast we do every week on at Dremio. And basically, actually tomorrow we'll be doing an episode where we're going to actually have NetApp come in and talk about how they really revolutionized like their setup using Dremio. I also do Select Star from Data Lake, which is a podcast I do with the other developer advocate at Dremio, Dipankar Mazumdar, talking about data lakes, and Data Nation, where I just, whenever I feel like I have something to say about data that I didn't cover in the other two, that's where it goes. And you can subscribe to all of these on Spotify and iTunes, as well as follow me on LinkedIn. But bottom line, when it comes to optimizing data, it really just comes down to sort of two things. Like you can always have faster queries in two different ways. You could either throw more processing power on at it, so you can always just get a bigger compute instance with more memory and more storage and all sorts of things. The problem is that costs more money. Okay, so you can optimize the job that way, but it costs more. Or you can optimize in a way that saves you money, which means read less data. So you can basically take different approaches to make it that when your query engine, like a Dremio or Presto or Spark, when they have to plan their query, that they read less data across less files. Okay. Bottom line is you're going to end up running less risk that you're going to have to do spilling data and have to write data to hard disk in order to complete the job, which is going to add time to the job. You're going to have less file operations where you have to reopen a file, read a file, then close the file when you're done reading it. The more we kind of reduce all these extra operations, basically the faster the query is going to be because the actual job has to do less. That's always the goal. How can we find out how to make this job do less to get to the same result? You're going to find that it's a lot faster, and it's also going to cost you a lot less in compute and storage and network costs. Okay, one way we can do this is we can take a look at the actual files that we store the data in. So typically, you're probably storing a lot of analytics type data in Parquet. And the reason why we like Parquet files is because it stores the data in sort of a columnar structure, because generally columnar structure lends more to sort of analytical type workloads. But a nice thing about Parquet files is that it's not just data in columnar format. What it does, it takes groups of rows and the columns in those rows and turns them into row groups. And then each row group has metadata associated with it. And the benefit of this is when you have a row group is that a query engine, again, like a Dremio, like a Spark, can look at the metadata for those row groups and say, okay, do I need to scan this chunk of the file? Okay, is this row group relevant to my particular query? Okay, this is referred to as predicate pushdown, being like, okay, this row group matters, this row group doesn't. So that allows an engine to be able to read a Parquet file faster. Okay, now the question is like, you want bigger, you can choose when you write a Parquet file how big these row groups can be. The question is, do you want them bigger or do you want them smaller? It could be either. Okay, the benefits of a smaller row group is that you can have much more granular metadata. Okay, so for example, imagine that I have data on people's height in one Parquet file, and then I sorted all that data based on the height. Okay, chances are only a few row groups in that file are going to have people of a particular height. So then when I filter based on height, it's more likely that more of those row groups can then get pruned from the query plan and make for a faster scan of that Parquet file. Okay, but what if I don't ever really filter on height, or I generally scan the whole Parquet file? Well, then what happens is that I'm slowing things down because every time it goes to a row group, it has to read the metadata for that row group. So if I'm not going to prune any of those row groups, then I prefer there to be bigger row groups, so that way I'm having to filter through like less metadata. So it just comes down to what your query patterns are. And a lot of this is going to come down to sort of like, hey, how do I query my data? So if I'm frequently pruning the data on very well-defined columns, then having row groups, more row groups can be very helpful. Also, but having bigger row groups, it can again make for a faster scan when I'm not necessarily going to be pruning a lot of those row groups as often. Okay, which may be for like a bigger table made up of many Parquet files, where honestly, probably many of the Parquet files are going to have data that are pretty much very similar on those fields, because it's a very, very big data set. So in that case, my concern isn't necessarily like pruning the individual row groups in those files more than pruning the files altogether. And that's where something like an Apache Iceberg would kind of be helpful, providing the metadata on the files. Okay, so, and then also you want to think about, okay, how big should the file be? Well, you don't want the file so big that it doesn't fit into memory. Okay, and then you start running into issues of having to do spilling, where it's going to have to write some data to disk in order to deal with sort of like not having enough memory, which again, having to write that data to disk takes time. So again, it just depends on sort of what you are, but what you're trying to do. But these are the kind of things that you can kind of improve and tune the performance of your job by thinking about how, okay, how are my Parquet files being written? What are the size of my row groups? What are the size of my files? And kind of tuning it from there. Then there's compaction. So again, if you're talking about a bigger table where it's not just one Parquet file, but like hundreds, thousands, millions of Parquet files, okay, in that case, the problem is you don't necessarily want a bunch of small files, because every individual file that has to be read by the query requires you to run an operation that opens the file, another operation that reads the file, and then another operation that closes the file once it's done with that file. Okay, so if I have 100 files, that's going to be 100 open operations, 100 read operations, and 100 close operations, versus if I had the data in 10 files, it would be 10 of each, okay, for the same amount of data. So this is where compaction comes in. So what you're doing is you're taking files that may be smaller than you'd ideally want them to be. So maybe you're targeting 1 GB files, which can be very typical for like, big data tables, and say, okay, hey, take any file that's less than a gigabyte and see if you can rewrite them into files that are at least, let's say, a gigabyte. Okay, so this way you are reading less files in total, okay, because more of the data is inside fewer files. So again, you're reducing those read operations, you're reducing those open operations, you're reducing those closing operations. Okay, so that's compaction. And then take big small files, turn them into big files. So I'd rather have, instead of having these 10 small files, have just one big file. I'm going to speed up that query because there's again less file operations. Now within those files, I may want to practice sorting, clustering. Okay, so right here, let's say here we have 3 Parquet files, and this is like, let's say, a field that we filter on. Okay, this is a particular column that we filter on the values they have. So let's say I'm running a query to scan for all the records where the value is A. Okay, before we did any sorting and clustering, well, there was at least one record that had a value of A in each file. Okay, so that means when we're doing the query planning, we're going to have to include all 3 of these files in the query plan. Okay, so in that case, it's going to scan all 3 files just to get that one record that it needs in each file. So that's 3 open operations, 3 read operations, 3 close operations. But if we sort or cluster the data, so that way data with similar values are generally in the same files based on our query patterns. Okay, we'll see it now in this case. Once we've clustered it, all the A records are in file 1 because there's only 3 of them. C, there was 4 records, so that got split up between files 2 and 3. But still, they're not in all 3 files; they're only in 2 files, so that's still better. And then the third file has all the U records. So now, if I wanted to scan for all the A records, I'm only going to need to scan 1 file. Okay, so by sorting my data, I've reduced the number of files I have to scan. Okay, and this is where things like Apache Iceberg or literally any table format, whether it's like Hoodie or Delta Lake, their metadata is going to allow an engine to know what kind of data is in each file. So based on like that table format's metadata, it'll know, oh, okay, file 1 only has 8 records. That's the only one we really need, and you can prune all the other data files from the query plan. So we basically save ourselves from having to read 2 files, and that's going to speed up the query quite a bit. Okay, because we're only just reading that 1 file, all the data we need is in there. Okay, so again, by having well-designed Parquet files, by making sure that our file we take all those small files and make them bigger files, and then taking what's inside those files and clustering it by values that we frequently query on, we're going to start seeing more and more improvement of basically the speed and performance of our queries. But just a straight up sort isn't the only way we can do this. Another approach to sort of sorting or clustering the data in those files is Z order. So in Z order, what you do is you take multiple fields. Okay, so in this case, we're going to pretend there's two fields, X and Y. And we're going to make four sort of categories. Because we're going to say that, hey, X has values between 0 and 100, and Y has values between 0 and 100. So we're going to say, hey, we're going to create 4 buckets, all the records that have an X value of 0 through 50, and a Y value 0 through 50 go in this bucket. And then we kind of split it up into 4 quadrants. And basically any data that fits into this bucket is going to be written to separate data files than records that fall into these other buckets. So essentially anything that matches these two truths, they're going to be in a separate data file than anything that isn't. This is very beneficial if my queries often filter by both X and Y. Because what's going to happen is that if I say, hey, I'm looking for records that have X25 and a Y25, well, that means the only data files I have to care about are the ones generated from this bucket. I can skip all the data files based on this data. I can skip all the data files based on this data. I can skip all the data files based on this data. So I've kind of gotten rid of that surface space by like 75%. Okay, theoretically, it's like all perfectly distributed. But even if I only filtered based on X, so if I said, hey, I only want X of 25, well, that still helps me out because now I'm only scanning records in this bunch and in this bunch. Well, no, I mean, in this bunch and in this bunch. Okay, so I've still reduced all the files from these two buckets pretty quickly. So that's the benefit of like Z order sorting. It kind of, since you generally query regularly by like 2 different fields or more, being able to sort of cluster the database on the values across multiple fields, it allows you for even more effective pruning of the data when you run a query. Okay. Now the thing about like clustering and sorting like we did in the previous slides is that when you're clustering, you may still have data with different values in the same file. So for example, here we sorted the data, but you see the file 3 still had data with C and U in it. Okay, so it's more clustered, but if I was scanning like for U data, then I'd still scan file 3 and there'd still be a C file record in there, which the reader would still have to kind of read over. But what if I'm regularly only scanning for one of these values? I'm only scanning for A records. I'm only scanning for C records. I'm only scanning for U records. Then I would really be better off if they were in just completely different data files, not just sorted across my data files as they are, but in completely separate buckets of data files. Okay. And this is where partitioning comes in, where you say, hey, all the data file, all the records with this value are going to be written in completely separate data files than any of the other ones. Okay. So if I were to partition here, like let's say based on age, the value of age, all the records that have an age of 10 will be written to separate data files. All the records with age 11 will be written to separate data files. And if that's a very typical query pattern for me, for like basic, like another example I like to use is always like imagine like a national politics database. Okay, chances are you might have like a state party apparatus that's going to filter based on state and say, hey, I want all the voters in Georgia. If I partition that data based on state, well, then only when they query, say, hey, give me voters from the state of Georgia, it's only going to query the Georgia partition because it'll know that, hey, these data files are just covering Georgia and that's it. Okay, and you can just immediately ignore all other partitions. Okay, so that's sort of the benefit of partitioning. It's similar in the sense of clustering. The difference is that it's not how the data is stored within the data file, is whether the different values are in completely different data files. Ideally, you do both, right? Ideally, like, okay, maybe my data is partitioned by age, and all the 10 records are in separate data files, but maybe from within there, I might still sort them by height or sort them by name, because maybe I typically say, hey, give me, all people above 6 feet who are age 10. That sounds like a weird query, but you get the point. Okay, so that's the idea there. The idea is you're just trying to structure and organize the data in a way that allows query planning to be able to prune more files more often for better performance. And there's different types of partitioning. I mean, in the previous one, we just said, okay, a value is a partition, but you can also do range partitioning where you say, hey, a range of values is within a partition. So we might say, hey, all ages between 10 and 15 are going to be in this partition. All ages 16 to 20 are in this partition, and all ages 21 through 25 are in this partition. This definitely makes a lot of sense when you have a field that has basically a lot of unique values. Okay, because it won't make sense. Like for example, like a timestamp, every second is a whole other value. So say it's partitioning by timestamp, basically you'll have a whole lot of one record partitions, which would actually end up slowing down your queries because you end up um, having in sort of too many partitions. So basically you have all these, you end up with that small file problem and you can't compact it because there's no more records in that partition for you to compact with. So essentially you just have a bunch of small files that have to get read, and then plus the way it has to like scan through more partitions. So it's just going to overall be a longer query because you chose a partitioning value that just has too many unique values. Um, and then you also could run into like a partitioning or data skew where you might have too much data in one partition versus another partition. And what happens there is that because if you scan that other partition, it's going to be slower than if you scan this partition. So you get kind of imbalanced query performance because your data isn't being like evenly spread across partitions. So that's another thing you want to watch out for. But that's more of like you notice that as you take a look at the performance of different queries and monitor the actual file size of the data in different partitions to see, hey, this partition is 10 gigs, but this partition is only 1 gig. Okay, I have data skew. Um, and then you rethink your partitioning to see if you can partition it in a way that more balances it out. But again, this is another way where you can try to avoid having smaller partitions. Then there's hash partitioning. So, if you use something like bucketing in Iceberg, where they have like this bucket transform, essentially that's what this is doing. Okay, so when you use like the bucket transform in Iceberg, what it does is you actually name like a arbitrary number of buckets. You say, hey, I would like all my data split across 20 buckets. And what it's going to do, it's going to use a hash function to evenly distribute the values in a particular column that it's bucketing by across these different partitions. So you might have, I might have data from like 1 and let's say A and D in partition 1. They're not necessarily sequential, but because of the way the value gets hashed, they ended up in partition 1. And this allows you to sort of more evenly distribute the data um, to avoid things like data skew, like I mentioned earlier, because you're using the hash function to sort of try to evenly distribute those values. So that's another approach to sort of how you decide, okay, hey, which records get written into which data files? Because again, partitioning, it's a segregation of data files. This data is in these data files. This data is in these files. Then there's composite partitioning, another way you can deal with data skew, where basically, let's say when I partition based on age, I got data skew because maybe there's just too many 10-year-olds and not enough 11 and 12-year-olds. But if I add another parameter, I may get a more even distribution. So maybe I say, okay, well, let's partition by age and height. And now, okay, the different size of different partitions, parts like the size of data files, become more evenly distributed. So that means the performance of queries across whatever partition are going to be much more consistent. Okay. And now, not only can there be about how you write your data files that's going to improve your performance, but also compression. Now, compression doesn't necessarily increase or decrease the amount of data that the actual records that have to be read. But what it does do is that a smaller file is going to have less bytes that need to be transferred over a network. So if you're talking about like a network of a cluster of computers that are running a query, whether it's a Spark cluster, a Dremio cluster, or something like that, that data, every time it moves from one machine to another, those are bytes going over a network. So if you have smaller files because you have good compression, you're transferring over less bytes over the wire. Those bytes can then the file can be completely loaded to its destination quicker, so that way you can get to the process of opening that quicker. So that's where like good compression comes into play. And there's many different, now the benefit is, again, with compression, you save money. And two, you might get faster reads depending on the actual compression algorithm you use, because it can, it's another thing you have to do when you're writing the data. So there's always trade-off. Okay, like anything you do to improve reads oftentimes has an impact on writes, because you're doing more work to prepare for the reads. And then oftentimes things that speed up writes oftentimes affect reads, because you're not putting together as many abstractions to speed up those reads. Okay, now if you want to read an article that I wrote about the different algorithms, the different compression algorithms, that's going to be located right here at this QR code. If you'd like to read that and kind of like see sort of like the trade-offs between the different like compression algorithms. Now here's just a few more topics also to think about when it comes to like optimizing data. One, there's also an approach of something called a materialized view. Okay, and recently a gnarly data way is one of those.
Hey everyone, I apologize for the technical difficulties. It looks like Alex is having some issues with the connection on his end. I'll message him, and we should be able to get this resolved and fix this shortly. Hey, Alex.
Creating a sort of
checking in with you here, Alex. Yep. You're getting some significant lag and compression yourself. I'd recommend leaving and rejoining the meeting to see if we can reset your audio here. Thank you. Yeah, thank you everyone for your patience. Alex will be back on shortly, and we'll be resetting his spot. Hey Alex, welcome back. Thank you, Alex. Welcome back. So I think we lost maybe a minute of your time there. So try to go back to just after you mentioned your article on compression and pick up there. Thank you.
Got it. Okay. It's going. Here we go. Okay, so yeah, so again, you can scan this QR code to learn a little bit more about different compression algorithms and how to use them. But some other topics to talk about. There's materialized views and reflections. Like I actually did a whole episode of gnarly data waves on this specific topic alone, because it's a big one. Now, first, let's just talk about what materialized views are. Okay, so materialized views are something you can find across many different engines and different tools when it comes to querying your data. And what it does is, let's go back to that whole politics example. So let's pretend that I have the database of all voters in the United States. Okay, but maybe for like the Georgia party apparatus, what I'd like to do is make it where they can query the data faster. I could partition it, but maybe I already have my data partitioned based on some other metrics. So maybe I have the data partitioned based on county or something. So what I want to do is create a specific abstraction of just the Georgia voters. So what I can do is I can create a materialized view, and what it does, it'll run the query for all the Georgia voters, and then literally make a copy of that data and then put it under a new namespace. So instead of me querying all voters, I would query something like GA_voters. Okay, so there'd be actually a separate namespace. Now it's going to be a lot faster for me to query that, because basically I'm only scanning that smaller materialized view. Like it's literally like a physically materialized data set. Now, the cons are, hey, I just made a copy of the data. So even though that's maybe a terabyte table, I may have just made a copy of a gigabyte worth of data that I already technically have in the original data set. So there's a con in storage. There's a con in the sense that you have to create this extra namespace. So now, if I'm one of those people in Georgia querying to get those particular voters, I have to know to query this other namespace, GA voters. If I don't know that and I still query all voters, I'm still going to get that much longer scan. Okay, and then if I want to create other versions, like let's say I only want to create, Macon County voters and whatnot, then I have to create another materialization, which creates another copy, and so forth and so forth. So that every time I create another materialized view, I'm creating essentially another copy, which may not necessarily be ideal. Okay, but it's still faster. Okay, at the end of the day, like it's still one way to improve performance. Now, unique to the Dremio platform, Dremio has a feature that kind of takes what you just saw with materialized views and takes it kind of to the next level. Again, I would go check out that episode of Gnarly Dataways for a really deep treatment of this. But what Reflections does is that instead of me creating a new copy under a new name, you basically turn on this feature on like the original data set. So all voters would have reflections turned on, and then I can create maybe like, let's say, instead of, it'll create a copy still, but it can create a copy with different sorting and partitioning rules. So I might create a copy that is partitioned by state instead. And now when someone queries the Georgia uh, for Georgia, they're just going to use that Georgia partition for that reflection. So that reflected copy will kind of handle that. And it's going to handle that for all states. Or what I could do is I can create a view, just a normal logical view, which is not a copy. So, so it would still be like GA underscore voters, but it'd be a logical view. I would turn on reflections on that. So it does make a copy of that Georgia data set. But again, I can suddenly like partition that by county. And then again, for that make in county query, they don't need to create a separate abstraction because that reflection will already be partitioned for that purpose. So it makes it where you can actually get, you don't necessarily have to have as many namespaces if you construct your models effectively, and you can get a lot more acceleration with a lot less number of copies. And you don't have as many namespaces, so people don't accidentally scan the whole table by accident because you're scanning the wrong namespace. So that's what Dremio Reflections brings to the table. And in essence, what it does, it automates a lot of the things that your pipelines would be doing on sort of like the tail end of your chain of pipelines. So getting rid of like a lot of that tedium out of that last bit. Again, shuffling distribution. So again, whether you're using Spark, Dremio, something like that, there are different operations depending on how you set up your job might result in more shuffling, meaning more moving the data across the different nodes on the cluster. And basically what you'd want to do is just kind of figure out, okay, what things am I, and you would do this query by query. So you would have a job and you were trying to speed up. You would want to analyze like the job. So like in Spark or in Dremio, you can generally see a job profile where you can kind of see like the steps the job is taking. And you would want to look for anywhere where data is shuffled and try to see, hey, is there a way I can do this job differently that might reduce that shuffling? Because the less the data has to move around, the faster it is. Okay, caching. Basically any kind of caching strategies. So this is going to be more something that's kind of built into different engines. So for example, using Dremio as an example, Dremio has this feature called the columnar cloud cache, where basically as you run queries, it'll pick up on sort of data, maybe data files or a portion of a data file that gets queried very often. So it might even just be like a row group that gets scanned very regularly. And what it'll do is it'll make a physical cache on the actual sort of the nodes in the Dremio cluster. So that way on future subsequent queries, it won't have to necessarily hit your cloud storage to get the file, to get those records anymore. And that speeds up the query, but also cuts down on network costs. So all those like network calls you'd be making to S3, it's going to cut down those costs, speed up the query, which cuts down the compute costs. So overall, it can save people quite a bit of money when they're taking advantage of that, when they're using like sort of Dremio to run their queries. And then the last topic will be serialization and deserialization. So the idea is that there's a cost every time your data transfers between different formats. So what would happen in the past is a lot of things were kind of the way we would transfer data would oftentimes be in sort of row-based formats, or a lot of, we might have the data in a file format that's columnar, but the actual tool we're using loads the data and then converts it to a row-based format or a different version of the columnar format. So every time you're switching formats, there's a cost to deserialize and serialize. So basically to get out of one format into another. And this is where like Apache Arrow really comes in and saves the day. And Dremio is built from top to bottom with Apache Arrow in mind. And there's a lot of tools nowadays, like when you think of like things like data fusion and whatnot that are incorporating Apache Arrow all over the place. But the benefit is that you'll have a format. The way that the data is represented in memory is going to be very similar to, let's say, the way your data is being formatted in a Parquet file. So the actual loading from a Parquet file to Arrow in memory is going to be there's very minimal cost doing that because it's almost the same. It's almost structured the same way. And then there's Apache Arrow Flight, which would replace, let's say, JDBC, ODBC, so JDBC ODBC, when you send data over JDBC ODBC, the actual data moves in a row-based format. So then what happens is that you might have the data processed in arrow, but then you have to convert it to row, and then on the other end, convert it back into columnar. Okay, and there's a cost every time you make that conversion. But if you use Apache Arrow Flight as the way you move data back and forth between these columnar sources and destinations, you get rid of that. So it stays columnar, and you get rid of that serialization, deserialization, which really, really saves you a lot of time, because again, you're not doing that conversion. Conversion is what cost is. So you can move lots of data really, really fast. So theoretically, again, if you have really well-structured files, again, files that are partitioned, sorted, with very idealized row groups, okay, scanning those files are going to be really fast because you're narrowing down the amount of data you need to scan. If you're minimizing your serialization and deserialization because you're using Apache Arrow-based tools, then once you figure out that smaller subset of files and row groups you need to read, you can move that data into memory a lot faster, process it a lot faster, and then move it to your local computer and your local notebook where you maybe or the local machine that's running the BI tool much faster. Okay, and overall you're going to notice better performance. A lot of these things are things that you can do when you tweak your own jobs by just like maybe writing your SQL differently or writing your Python differently. Some of these are optimizations that come from the engines that you use. Okay, so again, I point out the example of things like reflections and the columnar cloud cache. Those are features of Dremio, so it's more like the tool you choose that brings you the optimization than you having to sort of like tweak it yourself. But these are all different levers you can pull to improve performance when you need performance. With that concludes this presentation. Again, my name is Alex Merced. I'm a developer advocate at Dremio. Feel free to add me on LinkedIn and subscribe to the podcast that I have over there on, Spotify and iTunes. And with that, I'll open it up to Q&A.
Thanks so much, Alex. I'm going to open the floor for questions in the chat. Currently, there aren't any questions in the chat, but we might take a moment here. I would ask my own question here, which is generally when you're working with materialized views, what are some of your strategies for preventing some of the latency issues that often happen with those? Because I know some databases like Cassandra just have materialized views, but sort of recommend not using them by default. What are some of your strategies for having materialized views and having them work well in concert with the rest of your data?
I mean, I agree that this should never be your default. Like generally, when you run into those bottlenecks, then you think, okay, hey, is materialized views or something like Dremio reflection a solution for that particular use case? Now this is kind of like where with materialized views, I guess it just depends on how the particular query engine and whatnot, how they store the views and how they end up. And then also the issues oftentimes kept keeping the views in sync, materialized views in sync. But I guess that would depend on the database system. I'm less familiar with Cassandra personally to know exactly like how it's handling the materialized views under the hood. But I know in the case, these are the kind of situations where having Dremio as part of your stack, regardless of where your data lives, because Dremio is more of a data federation platform, so it doesn't actually store your data. So your data could be in Cassandra, it could be in Parquet S3, it could be in Postgres, it could be wherever, and then you can bring it into Dremio and then allow Dremio reflections to kind of handle that. So that way the user doesn't even have to think about whether they're using a materialized view or not. They can scan the actual table, and if the reflection would speed up the query, Dremio will figure that out. Like Dremio will do a cost-based calculation to say, okay, what happens if I use the reflection? What happens if I don't? And if it makes sense, they'll use it. And if it's not going to speed up your query, then it won't use it. And it just takes a lot of the thinking out of that. And it's one of the benefits of kind of having that as your access layer. So you'll have all your data sources and all your data pipelines behind the scenes, and then essentially all your sources, wherever the data is, you just connect to Dremio, and then Dremio can handle that logic and all those sort of end user bits. So that way the end users just focus on analyzing and running analytics on their data.
Thank you. We do have another question. This is from Will Angel. Great to see you in the chat, Will. So between reading too much data and reading too many files, can you talk more about the biggest mistakes you see the most often? Yeah, so I think this is a question about big data. Will, if you're seeing this, I think the follow-up in the chat is, are you talking about issues with sort of reading the data or processing here? But
Oh, yeah, I can talk to that. Like,
yeah,
there's one thing I seen a bit, not as much recently, but like in the early days of, let's say, like Apache Iceberg, when people use Spark, like Apache Iceberg, one of the things, like the way Spark will work. So basically, let's say you partition your database based on X. Okay, the way Spark works is that it's going to take all the records that you're going to write, okay, and then splits it into different sort of tasks or jobs, and then each job is sort of isolated, because it's going to be sort of a separate node that's writing it. So what happens is that they wouldn't sort the data that you're sending to all these nodes on the Spark cluster. So I might have records with I might have A, B, and C records sent to each job or each task. And so what would happen is that each job, or so basically each node, they're going to write a separate file for that A record, a separate file for that B record, a separate file for that C record, because they're partitioned based on that value. But because those records aren't all on the same job or the same node, they're not being written to the same file. So one of the things is just making sure that, like, there's a setting in Iceberg, then now it's the default value. Like, it was like a shuffle distribution, or I think it's called like distribution mode. Now, before, the default was nothing. It would allow you to kind of decide how you want to tune it. Now the default is hash. So by default, what it'll do is it'll hash based on your partition value. So when it's distributing all those records between the different tasks, it'll pass the value, the partition value, to that hash function and say, okay, well, let's cluster the jobs that hash out over here, and that way you're going to get a much more smarter distribution of those records across the different Spark jobs. So you're not writing as many files. So it's not just how you partition it, it's also essentially how the tool you're using, whether it's Dremio or Spark, because generally all these MPP or massively parallel processing tools are going to do the same thing, where basically each node is kind of doing their piece of the job with the data that's given to them. And you want to kind of know sort of how can I optimize how that data gets distributed. Sometimes just doing a sort. And then there's also, like, when you say sort, oftentimes, like, there's two concepts. There's a sort, like a sort before you distribute the records. And then there's like a local sort, doing a sort within each of those jobs. And each of those jobs individually get sorted. So like these little, like, understanding these things about the tools you're using with a Spark, Dremio, or any other kind of MPP system, knowing how you can affect those can sometimes help write the data more sensibly on the other side. And oftentimes, not appreciating those nuances can oftentimes has bitten a lot of people when they try to implement, particularly, especially like lakehouse patterns. And then you see, like, oh, why am I writing so many files when I try to write to X data table format? It's oftentimes just the tweaking of sort of like that, how the records are being distributed across the nodes.
yeah, great answer. Will, thank you for that question. It looks to me like there are not currently any other questions in the chat. So I really want to thank you for your time. Thank you, everyone, for being here. This is, again, 100 data engineers lunches. I know I've learned a lot by participating, presenting, and watching these lunches. Just, thank you to everyone who's presented in any of these 100, and especially Alex. Thank you for being here today.
Thank you. It's been an honor to be a speaker on number 100, and I look forward to seeing everyone again. Next time I'm back, I think, which probably will be next month. But
yeah, I believe that's set for November 2nd is my belief. I can double check that, but
okay.
But hey, thank you everyone so much for your time, and we'll see you next time.
No problem. See you all then. Thank you.